You also need to calculate this number for your design. In the double pipe heat exchanger, the heat flow is from the hot process water, through the inner pipe wall, to the cold cooling water. To determine the heat transfer coefficient for the cold film, H, you first need to calculate the Reynolds number of the cooling water in the annular space, between the outer and the inner pipe. D, H, is the hydraulic diameter of the annulus. In the diagram shown above, dark gray represents the cooling water squeezing through the annular space between the outer pipe and inner pipe. D, I, is the inner diameter of the outer pipe, and D, O, is the outer diameter of the inner pipe. D, H, is equal to, D, I, minus, D, O. Consider water flowing in the annulus at a velocity of u, which is equal to delta S divided by delta T. This corresponds to a flow rate of Q, which is equal to the volume delta V, divided by the same delta T. The volume, delta V, is equal to the cross-sectional area, A, x, times the length, delta S. Hence, you can see that the flow rate is equal to the cross-sectional area, times the velocity, and this allows you to calculate the velocity in terms of the mass flow rate, as shown. Without the inner pipe, the cooling water would experience the inner cross-sectional area of the large pipe. However, in the double pipe, the presence of the inner pipe reduces this cross-sectional area, by the outer cross-sectional area of the inner pipe. You need to determine the physical properties, viscosity, and density, at the average temperature of the cooling water, as specified in Table 8.4. This table contains the circular tube Nusselt correlations that you need to calculate the heat transfer coefficient, but using the hydraulic diameter instead of a normal diameter, as specified below the table.